Hi, everyone, and welcome to week 8 of Introduction to Logic. Today, we're going to be covering two additional proof methods called conditional proof and indirect proof. These two proof methods are fairly straightforward. I think you'll find they make a lot of proofs a lot easier. There are a few things to keep in mind when using them, but overall, I think you're actually going to find that you enjoy using conditional proof and indirect proof more than you've enjoyed learning the fairly complex rules of replacement over the last couple of weeks. All right, let's go ahead and dive in. The first new rule is called conditional proof, abbreviated ACP and CP. ACP stands for an assumption for conditional proof, and CP stands for conditional proof. The way it works is this. If you need to prove a conditional, like you see down here at the bottom of the screen, P implies Q. One way you can do that is to actually assume that the antecedent is true. So you can assume P is true. And then if you can show that Q follows from that, you will have shown that P implies Q. The way this works in the context of a proof is that you add the antecedent into the proof as a new assumption. But what you do, you use this vertical line, which I'm going to highlight in green right here, to indicate that everything else that follows is dependent on the assumption P. So it doesn't follow from the premises that are given, but it follows if you add the assumption P. And then after a series of steps, if you can show that Q follows from that, you will have shown that P implies Q. A very, very important thing to keep in mind about conditional proof and indirect proof as well is that when you're using these proof methods that allow you to introduce a new assumption into the proof, everything inside this vertical line, to the right of this vertical line that we're adding into the proof, doesn't actually follow from the premises unless you assume that P is true. That means that after you close off this assumption, once you've finished off your conditional proof to generate P implies Q from this indented series of steps next to this vertical line, that means you can't cite anything inside that vertical line once you've closed off the conditional proof and discharged the assumption that you've made. That sounds pretty complex, but I will show you what it looks like in the context of a real proof momentarily. But the key takeaways are this. If you can use conditional proof whenever you need to prove a conditional, either as the conclusion of a proof or even in the context of a larger proof, when you know you need a conditional but you don't see how to get it, you can often build that conditional this way. It works like this. You assume that the antecedent is true, use this indented line, this indented vertical line to show that everything else that follows is dependent on that assumption that you're making. If you can reach the consequent of that conditional on its own line, you can then close off your assumption and write P implies Q elsewhere in the proof. And basically, this conditional P implies Q is not actually dependent on whether P is true. It says if P is true, then you can get Q, which is why it works, even though you're assuming that P is true in order to generate that conditional. So we'll see what that looks like in the context of a proof here momentarily. Let's talk about the other proof method, indirect proof, abbreviated AIP and IP. That's assumption for indirect proof and just indirect proof. The way it works is this. If you know you need to get something in a proof, here, let's suppose we need to get not P. One way you can do that is to actually assume that P is true, which is what's going on here in the first line of this indirect proof. We're citing it as AIP, assumption for indirect proof. Then if we can show after a series of steps inside this indented vertical line that that assumption leads to a contradiction, and here I mean an explicit contradiction, something like Q and not Q. And it doesn't matter what that contradiction is. It doesn't have to be the same letter as the letter that you used or the statement that you used to generate the indirect proof. Any explicit contradiction, it could be A and not A, could be B and not B, could be even something like this, A and B and not A and B. Any statement and the conjunction of any statement and its negation, an explicit contradiction. Then you can close off that assumption line and you will have shown that that assumption has to be false. And I think this is pretty obvious. If you make an assumption and you show that that assumption leads to a contradiction, that guarantees that that assumption has to be false. So the important takeaways here is that when you need something in a proof, either the conclusion or some intermediate step of a proof, you can assume the negation of it or the opposite of that statement you need. So if you need not P, just assume P. And then if you can show that that leads to a contradiction, and again, I want to reiterate this, it has to be a substitutionist instance of this form right here. Q and not Q, some statement and the negation of that statement, what's known as an explicit contradiction. Then you will have shown that that initial assumption that you started the indirect proof with has to be false. And you can conclude the negation of that outside the scope of that vertical indented line. And you cited, oh, excuse me, I just realized I have a typo here, not CP. That would be indirect proof, IP, right here. Sorry about that. Okay, so these are fairly straightforward. Let's go ahead and dive in and do some proofs using these two methods. So in this first batch of proofs, we're entitled to use only conditional proof, and we're going to do another batch in the second part of the video that lets you use either indirect proof or conditional proof or both. But for these, we're going to try to stick to conditional proof, although I might mix it up just a little bit. Okay, so in this proof, we're given two premises. F implies E. The second premise says if F and E, then R, and we're just trying to show this conclusion, F implies R. So what I noticed right off the bat in light of the new rules is that this conclusion, F implies R, is a conditional, which means you can almost immediately think you're going to use a conditional proof here. So what I'm going to do, I'm going to add an indented line right here, starting with line 3. I'm just going to give myself a couple lines there. I'm going to assume that F is true, assume the antecedent of that conditional. And we're going to cite that as ACP, an assumption for conditional proof. So what I've done, I've assumed that that antecedent is true, and everything that follows now inside that vertical line is only going to be true if we assume that antecedent is true. And once we discharge our assumption, once we're done building that conditional, we'll no longer be able to cite any lines inside that vertical line. So the nice thing about conditional proof and indirect proof as well is they allow you to add an additional assumption into the proof. You can see that we've added F into the proof here, and that's really handy because that gives you something very easy to do with line 1. And I think you'll find that when you start using conditional proof and indirect proof, you end up using the fairly straightforward rules that you've learned up till now. You'll do a lot of modus ponens steps, modus tollens steps. You'll do some De Morgan's rule steps, other rules as well. But in general, you use a greater number of the easy rules. So these are fairly handy proof methods to have in your toolbox. Okay, so if F is true, we know that E has to be true from line 1. That's going to follow from line 1 and line 3. In fact, I'll use a different color here for clarity. That's going to follow from line 1 and 3 by modus ponens. So we don't actually know that E is true. What we're saying here is that if you assume F is true, then we know E has to be true as well. So again, just to make this explicitly clear, we don't actually know that F is true. We're assuming that F is true for the purpose of building this conditional F implies R, which is the conclusion of the argument. All right, let's keep going. So the goal here now, just to reiterate this, the goal now is to get the consequent of this conditional R on its own line inside this vertical line. When we've done that, we can then discharge our assumption, close off that vertical line, and we will be able to write that conditional F implies R on its own line inside the proof. Okay, once we have E, I think this is pretty easy to see. Line 2 tells us that if we know F and E are true, then we can get R, which is what we're looking for. But we first need to conjoin F and E together on their own line. So F and E, and that's going to follow now from line 3 and line 4 by conjunction. So you can see what I'm doing here. I'm actually citing lines inside this vertical line, but that's because I'm not done with this conditional proof. Once I finish the conditional proof, everything inside this vertical line will become locked and closed off, and you won't be able to cite it anymore. But for now, we're still inside the vertical line, so we can cite those statements just fine. Let's lengthen this line a little bit. So according to line 2, we said that if we know F and E, then we can get R by modus ponens. So here on line 6, I'm going to write R by modus ponens. That's going to follow from line 2 and line 5 by modus ponens. Now what I do, this is not in your textbook, but this is a really handy visual aid. I think you can see what's happened here. I've assumed that F is true. I've shown that if F is true, R has to be true as well. So now I can discharge this assumption line. And what I often do is I write this little horizontal line to indicate that I'm done with that vertical line. And that, to me, visually closes it off and makes it really clear that you can't cite anything from 3 to 6 at this point on. But what I can do here on line 7, and line 7 is going to be outside the scope of this vertical line. So we're back in a non-indented sequence here. We've shown that F implies R has to be true. Now here's how you cite conditional proof. What you do is you actually cite the entire vertical line, line 3 through 6. So here you have to be really careful, not 3 and 6, but 3 through number 6 by conditional proof, CP. And we're done. We've shown that F implies R has to be true. F inside R, again, has to be outside the scope of that vertical line, because everything inside the vertical line we don't know is actually true. But once you're done with the conditional proof and you closed it off and you've generated this conditional, F implies R, we know that that conditional, if F then R, has to be true, no matter whether F is true. Okay, so this is a very textbook example of a conditional proof. Let's do another one. Okay, so I've got two premises. First one is fairly complex. It says, if either G or H, then S and T. Line 2 says, if either T or U, then C and D. And we're trying to prove this conditional here, if G, then C. And because the conclusion is a conditional, I'm going to immediately think conditional proof. I'm going to try to generate that conditional by conditional proof. So what I'm going to do, I'm going to add a line, line 3, but I'm going to add this vertical line to indicate that I'm going to make a new assumption. And I'm going to assume the antecedent of this conditional, G. And I'm going to cite it as ACP, Assumption for Conditional Proof. Now again, just to reiterate, the goal now is to get C on its own line inside the scope of that vertical line. If I can do that, I will close off that assumption, discharge that vertical line, and I will have shown that the conditional G implies C has to be true. In other words, I will have shown that if you have G, then you can get C. Okay, this should be pretty straightforward. This is going to be mostly review at this point. I see on line 1 that if I have a disjunction, G or H, then I could do a modus ponens step. Well, I have G, so I'm going to use addition to add H onto G, G or H by addition. So line 3 by addition. Then, like I said, we can do modus ponens to get S and T on its own line. And that's going to follow from line 1 and line 4 by modus ponens, MP. Don't forget to continue this vertical line until you're done with it. It's very easy to forget that. Okay, the next thing I see, again, I'm looking to get C here, and I see C stuck inside the consequent of this conditional on line 2, which says to me that if I could get that antecedent, T or U, then I could do a modus ponens step to get C and D, simplify it to get C, and I'd be very nearly done. But here on line 5, I've got S and T with T on the right side of that conjunction. I need to do commutativity to get T on the left side of that conjunction. So I'm going to reverse that and rewrite it as T and S. And that's going to follow from line 5 by commutativity. Don't forget those little steps. I will ding you for those on your homework if you forget those. Then, like we said, we're going to simplify to get T. That's going to be line 6 by simplification. Don't forget to continue your vertical line. We're not done with it. We'll only be done when we get with that when we get C on its own line. Okay, we said once we got T, we could do another addition step to add U onto T to get the antecedent of that conditional up here on line 2. So I'm going to add U onto T from line 7 by addition. Okay. Still continuing our vertical line, line 9. Then we said we could do modus ponens to get C and D on its own line, still inside the scope of that vertical line. So again, I'm going to say this multiple times because I really want to drive this point home. Everything inside that vertical line you don't know is actually true. It's only true if you assume that G is true. But if you assume G is true, we know that C and D would have to be true. And that's going to follow from line 2 and line 8 by modus ponens. Okay, we said the goal here is to get C on its own line, which we can do now because we have C and D. So we're going to simplify to get C on its own line. number 9 by simplification. Now look what we've done. We started out by assuming up here in line 3 that G is true. We've shown that if we assume G is true, C follows from that. So now we're done with our assumption line. We're going to close it off, which again, that's not in the textbook, that little horizontal line to close off the vertical line, but it's such a helpful visual aid. I highly recommend you do it. Makes your proof a lot easier to see visually. Okay, now we're back outside the scope of that vertical line on a non-indented line. And we're going to write G implies C. We've shown that the conditional G implies C has to be true. And that's going to follow now from everything inside this vertical line, from line 3 all the way down to line 10. 3 through 10, not 3 and 10, but 3 through 10 from conditional proof CP. And we are done. We've shown that that conclusion follows. So again, the key takeaways here, if you're trying to prove a conditional, you assume the antecedent is true inside the scope of this vertical line, which I'm going to highlight in pink now, right here. Try to show that the consequent follows inside the scope of that vertical line. Close off your assumption line, and you can write that conditional G implies C. The key thing here is that you cite everything inside that vertical line, line 3 through 10, and from this point on, if this were part of a longer proof, you would no longer be able to cite anything from lines 3 through 10. They would be closed off for use later in the proof. And we'll see how this comes up in a more complex proof here in a few minutes. Okay, in this proof, we are given 3 premises. Premise 1 says J implies that K implies L. Line 2 says J implies that M implies L. Line 3 says L is false or not L. And the conclusion says if J, then it's not the case that K or M. What I notice right off the bat, I'm going to highlight it right here, is that the main operator of this conclusion is a horseshoe. So this is a fairly complex conditional. And whenever you have a conditional like that, you can use conditional proof. All right, so what I'm going to do, I'm going to start by adding a vertical line, an indented vertical line right here. And I'm going to assume the antecedent of this conditional. So I'm going to assume J is true. And that's going to follow, actually it doesn't follow from anything. You just cited ACP, assumption for conditional proof. Now the goal, just to reiterate this, you start out by assuming the antecedent, and we're trying to prove that the consequent follows. So I'll be done with this indented conditional proof sequence, when I get the consequent of this conditional. It's not the case that K or M on its own line inside the scope of that vertical line that I added. All right, let's go ahead and dive in and see if we can figure out how to do that. Assuming J gives us a couple of obvious steps, I think it's pretty clear now that you can do modus ponens with line 1 and also with line 2 together with line 4. So let's do modus ponens with line 1 and 4, and that will give us K implies L. And that's going to follow from line 1 and line 4 by modus ponens. And let's do the same thing with line 2 and line 4. And that will give us M implies L. That's going to follow from line 2 and 4 by modus ponens. So you can see we're doing pretty easy steps at this point, just a couple modus ponens steps to get started. So conditional proof and indirect proof often will make many proofs much easier. Okay, the next thing I see, again, don't forget to continue your vertical line here, is that we have a couple of conditionals on line 5 and 6, K implies L and M implies L. And we know that the consequent of those conditionals, L, is false because of line 3. So I'm going to do a couple of modus ponens steps. I see that I could do modus tollens with line 3 and 5, and that will give me not K. So that's going to follow from line 3 and line 5 by modus tollens. And I'm going to do the same thing with line 3 and 6, and that will give me not M. Line 3 and 6 by modus tollens. Okay. So keep in mind what the goal is here. The goal is to get the consequent of this conditional. It's not the case that K or M. I'm going to do a little bit of scratch work here on the right. So we're trying to get, it's not the case that K or M. But by De Morgan's rule, that's just equivalent to not K and not M. So if I can get not K and not M together, I can just do a De Morgan's rule step and get what I'm looking for, the consequent of this conditional. It's not the case that K or M. So with that in mind, I'm going to erase this here. With that in mind, I'm going to conjoin not K and not M together. And that's going to follow from lines 7 and 8 by conjunction. Okay, still continuing our vertical line. By De Morgan's rule, we said that's equivalent to it's not the case that K or M, which is what we're looking for. That's the consequent of the conditional that makes up the conclusion. So this is going to be line 9 by De Morgan's rule, dm. So now look what we've done. We started out by assuming, in fact, I'll use a different color to indicate it here. We started out by assuming J was true. We've shown that that leads to the consequent of that conditional. It's not the case that K or M. So what I can do, I can close off my assumption line. I'm going to draw this nice friendly horizontal line to indicate that I'm done with my conditional proof. On line 11, outside the scope of that vertical line, I've shown that if J is true, I can get it's not the case that K or M, which is the conclusion of this proof. So if J, then, excuse me, made a typo there. If J, then it's not the case that K or M. And that's going to follow from everything inside that vertical line. In fact, I'll use the same color I've been using. That's going to follow from line 4 through 10 by conditional proof, CP, and we're done. So again, just to reiterate, I know I'm going to say this several times in the course of this video, but we don't actually know that everything inside that vertical line from line 4 through 10 is true. Those statements are true only if you assume that J is true. But that conclusion, J implies it's not the case that K or M is not dependent on whether lines 4 through 10 are actually true, because that's what a conditional means. If you assume something, then you can get something else. So it doesn't actually matter whether J is true. That conditional will still be true. If J were true, then I know I could get it's not the case that K or M. But once I've closed off this vertical line with my horizontal line between lines 10 and 11, I'll no longer be able to cite anything from line 4 through 10. Those are closed off for use later in the proof. Okay, let's do another example. Okay, so we've got 3 premises here. P implies that either Q or R. 2 says P implies R implies that S and T. 3 is if Q then R, and we're just trying to show the conclusion T. Now what stands out to me here is that the conclusion is not a conditional. So we're not going to use a conditional proof to get T directly, but I guess we're probably going to use conditional proof somewhere inside in the middle of this proof as an intermediate step to get a conditional that we're going to use that will eventually lead to the conclusion. So let's go ahead and dive in. What I see right away is that the antecedent to the conditional in line 2 right here is itself a conditional, right? Line 2 says, if you know P implies R, then you can get S and T. Well, I don't have P implies R yet, but that's a conditional. And I notice that if I assume the antecedent of that conditional P, then I can probably do a modus ponens step with line 1. So I'll probably be off and running. So let's go ahead and give that a try. So on line 4, I'm going to introduce my vertical assumption line. And here I'm trying to get P implies R so I can move forward in this proof and not be stuck. I'm going to assume that P is true. That's going to be an assumption for conditional proof. And what I'm trying to get, I'm just going to highlight it right here in pink. I'm trying to get R on its own line inside the scope of this vertical line. Once I get that, I can close off my conditional proof, get P implies R, and then I can do the modus ponens step as I've been describing. Okay. Well, once I have P, I know that Q or R would have to be true. And that would follow from line 1 and 4 by modus ponens. Okay, the next thing I see, this is going to look a little convoluted, but what I see is that I now have a disjunction on line 5, Q or R, and I know that Q implies R. If I had something like R implies R, Then I could do a constructive dilemma that would give me R or R, which would just be R, which is what I'm looking for. So what I'm going to do, I'm going to go really slowly here. In order to be able to do that, I'm going to need R, I'm going to write it off to the side here. R implies R, which is itself a conditional. So I'm actually going to do another conditional proof right inside this one. So now I've got one conditional proof going on inside the other, and I won't be done until I close off both of these conditional proof lines. So I'm going to assume R. I'm going to cite it here as another ACP. Then I could do something like this. From R, I can get R or R by tautology. You don't have a rule that lets you rewrite a line from above elsewhere in the proof. Some proof systems, some textbooks let you actually rewrite a line that you've encountered previously later in the proof. It's usually called something like reiteration or the reiteration rule. Here, this book doesn't have that, so we have to go through this kind of wonky tautology step in order to be able to build this conditional R implies R. So again, don't forget about your vertical lines. We're inside the scope of two conditional proofs now. And from R or R, we can just get R again from line 7 by tautology. Now look what I've done. I'm still inside the scope of this outer vertical line, but I've shown that if I assume R, I can get R. And that's going to follow. So from that, from line 6 through 8, I've shown that R implies R. That's going to be line 6 through 8 by conditional proof. Again, you're still inside the scope of this outer vertical line, and we're not done until we've discharged both of these conditional proof lines. If you manage to get the conclusion T on its own line, but you're still inside the scope of this vertical line, you're not done yet because you don't actually know that anything inside these vertical lines is actually true. Okay, now I said that what I could do, let me get back to my original color here. I said that what I could do, I said I could probably set up a constructive dilemma. So I have Q or R on line 5. I know that Q implies R. I know that R implies R. So what I'm going to do, I'm going to conjoin line 3 and line 9 together. So we're going to get Q implies R and R implies R. And that's going to follow from line, let's see, line 3 and 9 by conjunction. I'm still inside the scope of this vertical line. We have to keep extending this till we're done. Remember what we were trying to do. We started out trying to assume P so we could get R on its own line inside the scope of that vertical conditional proof line. So I'm going to do constructive dilemma now with lines 5 and 10, right? Line 5 says either Q or R is true, but line 10 says each of those two disjuncts, Q and R, implies something. Q implies R and R implies R. So that means that either R or R would have to be true. And that follows from line, let's see, that would be line 5 and 10 by constructive dilemma. Okay. Of course, R or R is just R. So on line 12, I'm still inside the scope of this vertical line. I'm going to keep extending it as I go. We're just going to get R from line 11 by tautology. And now look what's happened. I've shown that if I assume P, I can get R. So I'm going to close off, let's use a different color. I'm going to close off this vertical assumption line. I'm going to continue over here because I ran out of room. Line 13, outside the scope of that vertical line now, I'm done with that conditional proof line. I have P implies R. And that's going to follow from line 4 through 12 by conditional proof, CP. And this is a really nice result because now I have the antecedent to that conditional on line 2. I think that's really clear right here. The antecedent of line 2 is P implies R. And if you get that, which we just got on line 13, we know that S and T would have to be true. And that's going to follow from line 2 and line 13 by modus ponens. Of course, we're trying to get T. So we need to do commutativity, line 15, T and S. So that's line 14 by commutativity. And we're going to simplify to get T on its own line. So line 15, simplification, and we are done. We've shown that T has to follow. Okay, so this is a really interesting proof because it illustrates the way in which one conditional proof can reside inside another, or an indirect proof can lie inside of a conditional proof, or you can use conditional proof inside of an indirect proof, so on and so forth. Whenever you need a conditional, you should immediately think, could I get this by conditional proof? Here we said, at the very beginning of the proof, we said that if we could get the antecedent of this conditional, P implies R, then we could get S and T, and we just simplify T out, and we'd be done. All of this proof hinged on how to get P implies R. So we started out by assuming P. The goal was to try to get R on its own line. But notice what happened here. In order to be able to get R on its own line, I figured out that I had to get R implies R first. So I created another conditional proof sequence from here on lines 6 through 8, which I'm going to highlight in blue right here. Now I do have R on those lines, but I don't have R inside the scope of the same indented sequence that line 4 starts, right? It's inside yet another indented sequence. So I don't actually know that those are true yet. It's only when I get R inside the scope of that same indented sequence that line 4 started that I can close off that conditional proof line and get P implies R. So this is a fairly complex proof. You'll encounter cases like this where you need to do one conditional proof inside of another, or an indirect proof inside of a conditional proof, and so on. The key, of course, is that once you close off these conditional proof lines, so here from lines 6 through 8, once I've closed that off to get R implies R, I can no longer cite lines 6 through 8 because I don't know that those are actually true. They're all dependent on that new assumption on line 6 that I added. Okay, let's move on. In this example, I've got two premises. C implies A and D. Line 2 says B implies A and E. And we're trying to show this conclusion, C or B implies A. I think this is actually simpler than the previous example. What I see is that the conclusion is a conditional. It says, if C or B, then A. So I'm going to try to get this by conditional proof. So I'm going to start a new line. I'm going to start a vertical assumption line to indicate that I'm making an assumption, and I'm going to assume the antecedent of this conditional, which is C or B. And I'm going to cite it as ACP, an assumption for conditional proof. I think this is pretty straightforward from here. I see that I have a disjunction now, C or B, and I see that I've got two conditionals that correspond to those disjuncts. C implies something and B implies something. So I'm going to set up a constructive dilemma step, but to be able to do that, I have to conjoin lines 1 and 2 together. So this is going to be fairly lengthy because I'm going to have to add some square brackets. So C implies A and D, close that bracket, and another bracket. B implies A and E, and close that bracket. And that's going to be lines 1 and 2 by conjunction. Line 5, still inside the scope of this vertical line. I can do constructive dilemma, and that will give me A and D, or A and D. A and D, or A and E. And that's going to follow from line 3 and 4 by constructive dilemma. Okay, to me, line 5 looks an awful lot like one of the forms for the distribution rule. And it's common when you are doing conditional proof and indirect proof that you won't need distribution. This is a case where you actually do probably need to use distribution, although there's probably other ways you could do this as well. So if I did distribution, I would get A and either D or E. From line 5 by distribution. And that's a pretty happy result because the goal of assuming C or B was to get A on its own line. That's how a conditional proof works. You start out by assuming the antecedent. So in this case, we're assuming C or B, and we're trying to prove that the consequent A follows from that. Well, I just did that. Still inside the scope of this vertical line, because I can simplify A now and get A on its own line. So this would be line 6 by simplification. So what I've done, I started out by assuming C or B. I've shown that A follows from that. So I am now done with my conditional proof assumption line. I'm going to close that off. And here outside the scope of that vertical line, I've shown that if you have C or B, then you can get A. And that's going to follow from line 3 through 7 by conditional proof. And this was a pretty straightforward short proof. Okay, next example. Excuse me. So we only have one premise, if F, then G and H, and we're trying to show this conclusion. If A implies F, then A implies H. So what I'm going to do, I'm going to do a conditional proof, start out by adding a vertical assumption line, and I'm going to assume the entire antecedent of this conditional, A implies F. So when you're doing conditional proof, you have to make sure that you're assuming the right thing. You assume the antecedent of the overall conditional you're trying to prove. We're trying to prove this overall conditional right here, that horseshoe that I indicated with the arrow. So we're going to assume everything on the left side of it, that entire antecedent, A implies F. And that follows from assumption for conditional proof. Okay. Now, look what I'm trying to prove. I'm trying to prove another conditional, A implies H. And because that's a conditional, I can do another conditional proof right inside this one to get that second conditional that I need. So on line 3, I'm going to introduce another vertical indented proof line, and I'm going to assume the antecedent of this conditional that I need. If I need A implies H, I'm going to assume A right here on line 3. So another ACP, assumption for conditional proof. And then what's the goal? The goal is to get H inside the scope of the second line. That will give me A implies H. And then I can close off that outer, the first indented proof line to get A implies F implies A implies H. So if that's not clear what the strategy is here, let's do this proof. And then you might have to see the structure after it's done to see why I've done what I've done here. Okay, once I've got A on its own line, I can obviously get F from lines 2 and 3. And the reason I can cite line 2 inside line 3, the vertical line that starts on line 3, is that I haven't closed off line 2 yet, so I can still cite that later in the proof. Once I've closed off those vertical assumption lines, I can no longer cite anything inside those. But for now, those are still open, so I can cite those. That will follow from lines 2 and 3 by modus ponens. Once I have F, I can do modus ponens together with line 1 to get G and H. So line 1 and 4 by modus ponens. Now remember, the goal here we said was to get H on its own line. So I've got to do a couple little steps here to be able to get H on its own line. Don't forget to extend these vertical lines down. We can do commutativity to get H and G. So line 5 by commutativity. Then I can simplify to get H on its own line, still inside the scope of these two vertical lines. So H, that's going to be simplification from line 6. Now we said the goal was to get H inside the scope of this second vertical line, which we just did. So I'm done with this inner vertical line. But notice this, you have to be really careful here. I'm still inside the scope of that outer vertical line that I started on line 2. So line 8 will be A implies H. And that's going to follow from line 3 through 7 by conditional proof. Now remember how we started. We said we started by trying to assume the antecedent of this conditional. A implies F. Here, I'll use a different color. A implies F. And then the goal was to get A implies H inside the scope of that vertical assumption line, which we just did. On line 2, we have A implies F. We've shown that eventually if we assume A implies F, we can get A implies H. So we are done with this outer indented sequence right here. On line 9 now, outside the scope of both of those lines, I've shown this. If I start out by assuming A implies F, then I can get A implies H on its own line. And that follows from line 2 through 8 by conditional proof, CP. And this is a very elegant, beautiful example of how to use one conditional proof inside of the other. So if you need to, pause here and see what I've done, but I'll talk through it really quickly. I started out by saying, I need to prove this overall conditional indicated by this arrow on top of this horseshoe. So I'm going to assume A implies F, which I did here on line 2. Then the goal was to get A implies H. But that's a conditional too. So I said, well, to get that, I'm going to assume A, which I did here on line 3. Then I'm going to try to get H on its own line, which I did on line 7. So I closed off that conditional proof to get A implies H on line 8, still inside the scope of that outer vertical line that I added. And then that shows that if I assume A implies F, I can get A implies H, and I can close off each of those conditional proof sequences and get that conclusion on line 9. So fairly straightforward, but if you need to, pause and reflect and study this and look at similar examples in your textbook of how one conditional proof sequence can be used inside the other. Okay, this is a fun example. We have two premises. F and G is equivalent to H. Line 2 says F implies G, and we're trying to show this conclusion, F is equivalent to H. To get started, I want you to keep in mind what a biconditional is. It's a conditional that goes both ways, right? According to the equivalence rule, F is equivalent to H means that F implies H and H implies F, right? That's what equivalence means. So if I'm trying to prove that equivalence, that biconditional, I'm going to need to get these two conditionals first, F implies H and H implies F. So this says to me that I'm probably going to do two conditional proof sequences, not one inside of the other, but one after the other. I'm first going to try to prove F implies H. Then I'm going to do another conditional proof sequence to show H implies F. Then all I have to do is conjoin them together, use the equivalence rule, and I will get that conclusion. So let's try that strategy. On line 3, I am going to assume that F is true, ACP. And the goal now is to get H on its own line inside that vertical sequence. So let's see how I can do that. On line 2, I notice that F implies G. So from lines 2 and 3, I can get G. That's going to follow from lines 2 and 3 by modus ponens. Then if I can conjoin F and G together, that will give me H, but I first have to apply that equivalence rule to line 1. So this is going to be a fairly lengthy line. I'm going to try to keep this condensed, but I'm going to have this. F and G implies H, and H implies F and G. And that's going to follow from line 1 by equivalence. Giving myself a little scratch room there because I think this is going to be a fairly lengthy proof. Okay, I'm still inside the scope of this vertical line. So I'm going to need the left side of this, right? F and G implies H. So I'm going to simplify that, get F and G in parentheses implies H. That's going to be line 5 by simplification. So I have F and G, so I'm then going to conjoin F and G together. That's going to follow from line 3 and 4 by conjunction. And that will give me what I was looking for, which is H by modus ponens. That should all be review at this point. So that's line 6 and 7, modus ponens. Okay, that's half of what I need. I said that I can first prove that F implies H, which I've done. I've shown that if I assume F, I can get H. So I'm going to close off this vertical assumption line. On line 9 now, outside the scope of that, I can get F implies H. And that's going to follow from line 3 through 8 by conditional proof, CP. Now I'm only half done, right? That's only half of what I need. The other half of what I need is H implies F. So what I'm going to do, rather than continuing right there, I'm going to actually start a new assumption here on line 10, off to the right, and I'm going to assume H. And the goal now is to get F inside that vertical assumption line, the new one that I added. Again, this is not inside the scope of the first one. I closed off the first one after line 8 to get F implies H. This is a subsequent conditional proof step for the purpose of proving the other conditional H implies F. Okay, so line 11 now. We're going to kind of do the same technique, but I can't use line 5 because line 5 is stuck inside that conditional proof sequence. In fact, in retrospect, I probably should have done that equivalent step first, so it's not inside the scope of a conditional proof sequence. But this illustrates a really important point, that because line 5 is stuck inside this vertical line that I've already closed off after line 8, I can no longer refer to line 5, which means that if I need that again, I have to do that equivalent step one more time inside this second conditional proof sequence. So this is fairly lengthy. I'm going to try to write this as small as I can. F and G implies H, and H implies F and G. And I ran out of room there, so I'm just going to cite it right below. That's going to follow from line 1 by equivalence. Okay. Line 12, still inside the scope of the second vertical line that I added. I'm going to need the right side of that conjunction this time. I need to show that H implies something because I have H on line 10. So I first need to do commutativity. So I need to rewrite line 11, reversing the order of that conjunction. So another fairly lengthy line here. H implies F and G, and F and G implies H. And because I ran out of room, I'm going to cite it below. So this is going to follow from line 11 by commutativity. Okay. Line 13 now, I'm going to simplify to get H implies F and G. Line 12 by simplification. I have H, so I can get F and G now by modus ponens between lines 10 and 13. And remember the goal here, the goal was to get F on its own line, which I can do right now, still inside the scope of this vertical line. So line 15 will be F, and that will follow from line 14 by simplification. And now look what I've done over here. I've shown that if I assume H, I can get F on its own line. So I'm going to close off that vertical assumption line. And line 16, outside the scope of that vertical line, will be H implies F. And that's going to follow from line 10 through 15 by conditional proof. Now I'm not quite done, but I want you to see what I've done so far. I've shown that if you assume F, you can get H. I'll circle them in blue. Over here on line 9, if F, then H, and that followed from lines 3 through 8 by conditional proof. And it works the other way around. I've shown here on line 16 that I can get H implies F, and that follows from line 10 through 15 by conditional proof. I said that what I needed to do to prove the overall conclusion was take those two conditionals, conjoin them together, and use the equivalence rule to turn it into a biconditional. So I'm going to scroll down just a little bit here to give myself a little more room. So you can still see the conclusion up here. I'm trying to show that F is equivalent to H. So on line 17, I'm going to get F implies H. That was our first conditional that we got back here on line 9. And H implies F. And that's going to follow from, let's see, that's going to follow from line 9 and by 16 by conjunction. And the very last step, because F implies H and A implies F, here on line 18, we know that F is equivalent to H. which, sorry to have to scroll a bit here, but the conclusion of our original argument back here was F implies H, which I just proved, and that's going to follow from line 17 by equivalence. And we're done. Took 18 steps. So this is a very handy example of how you can use two conditional proof sequences back to back to prove a biconditional. That's what a biconditional means. If F is equivalent to H, that means F implies H and H implies F. So we use the two conditional proof sequences back to back to prove each of those two conditionals. So that's a quite interesting example. Fairly lengthy proof, but not too bad, I think you can see. Okay. Next argument, we've got three premises. Q implies that R implies S. Q implies that T implies not U. U implies either R or T. And we have the conclusion, Q implies that U implies S. So let's dive in. The conclusion is a conditional. The antecedent of that conditional is Q. So I'm going to start a conditional proof sequence with the antecedent of that conditional as the assumption. So I'm going to assume Q by ACP, assumption for conditional proof. Now I want you to talk through the reasoning here. You assume Q so you can get that U implies S. That's the goal that you're trying to get inside this vertical sequence we just started. But that itself is a conditional. Notice that U implies S is another conditional. So we could try to get that by doing another conditional proof inside the first one. And we're going to assume the antecedent of that conditional, which is just U. Don't forget to add your vertical lines, like so. And this is going to be another ACP, assumption for conditional proof. Now the goal here, I just want to highlight it with another color. The goal here is now to get S inside the scope of that second indented sequence. If I can do that, I will have shown that U implies S. When I close that one off, I will have shown that Q implies that U implies S. So once we get S inside these two sequences, we can just close off these two conditional proof sequences and we're done. So this should be pretty straightforward, I think. Line 1 and 2 says that Q implies something. So I'm going to do a couple modus ponens steps to start here. I notice that I can get R implies S. That's going to follow from line 1 and line 4 by modus ponens. And I notice, still inside these two vertical sequences, that I can get T implies not U. And that's going to follow from line 2 and 4 by modus ponens. Now we have U, which we added on line 5. Again, we can cite anything above because we haven't closed either of these assumption lines yet. So on line 8, still inside the scope of these two vertical sequences, I'm going to get R or T by modus ponens, right from line 3 and 5, MP, modus ponens. Okay, what I see now is then I have a disjunction, R or T, but lines 6 and 7 tell me that each of those two terms implies something. R implies S and T implies not U. So I am going to set up a constructive dilemma. First thing I need to do is conjoin 6 and 7 together so it matches the form for constructive dilemma. So we have R implies S and T implies not U. And that's going to follow from, let's see, 6 and 7 by conjunction. Now, if I do a constructive dilemma step, again, every time I do this, I have to remember to bring down these two vertical lines. I haven't closed them off yet. Make sure you don't forget to do that when you're doing your homework assignments. From constructive dilemma, I can get S or not U. And that's going to follow from line 8. Oops, use a different color. Line 8 and 9 by CD. Okay, what I'm going to do, because I kind of ran out of room, I am going to continue this over here on the right, line 11, and I'm still inside the scope of two conditional proof sequences. Okay, I'm trying to get S. I have S or not U, but I know U is true. So this is starting to look like a disjunctive syllogism to get S. The first thing I need to do is I need to have not just U, but I need to have not U. So I have the negation of one of those terms in one of those two disjuncts on line 10. So that's going to be line 5 by double negation. Also, that disjunction on line 10 is in the wrong order. The term that I have the negation of, not U, needs to be on the left. So I need to do commutativity on line 10. So on line 12, I'm going to rewrite line 10 as not U or S. So that'll be line 10 by commutativity. Now I can do that disjunctive syllogism step. Again, here, still inside these two vertical lines. Don't forget to bring them down. I can get S on its own line, and that's going to follow from line 11 and line 12 by disjunctive syllogism, ds. Now, remember how we started out this proof. We started out by assuming Q, trying to get U implies S, but we said, well, that's another conditional. So we're going to assume U and then try to prove S, which we just did. So I'm going to close off this inner conditional proof sequence, still inside the scope of the outer one. Here you have to be really careful not to forget about that outer sequence that you're still inside of. So line 14, I've shown that U implies S inside the scope of that outer conditional proof sequence. So that's going to be line 5, everything through line 13 by conditional proof. And now look what I've done. On line 4, I started by assuming Q. I've shown that if I assume Q inside the scope of that outer initial vertical sequence, I can get U implies S on line 14. So I am now done with that conditional proof sequence. And on line 15, outside the scope of both sequences, so we're back on a non-indented line now, I've shown that if Q, then I can get U implies S. And that would follow from everything from line 4 all the way through line 14 by conditional proof, CP. And we are done. Okay, so this is another really great example of how to use two conditional proof sequences inside the other when you have conditionals nested in each other, like you see in the conclusion of line, the conclusion of this argument, next to line 3. Okay, let's do some more. Here we've got 3 premises. E implies that F implies G. H implies that G implies I. Line 3 tells us that if you have F implies I, then you can get J or not H. And we're trying to show this conclusion. E and H implies J. So what I'm going to do, I'm going to start out by doing a conditional proof sequence. Right, the conclusion is a conditional. If E and H, then J. So I am going to start a conditional proof sequence. I'm going to assume E and H, the antecedent of that conditional. And that's going to be ACP, assumption for conditional proof. Now, the goal now is to get J on its own line inside that vertical sequence. Okay, what I see is that each of those two terms, E and H, correspond to the antecedents of the conditionals on lines 1 and 2. So I'm going to simplify E and H out. So I can get E right off the bat, line 4 by simplification. But to get H, I have to do commutativity first. H and E. Line 4 by commutativity. Okay, now I can get H on its own line. Line 6 by simplification. And now we can do those modus ponens steps that I mentioned with lines 1 and 2. So I'm going to add line 8, still continue my vertical line. Let's see, from line 1 and 5, I can get F implies G. And that's going to follow from line 1 and line 5 by modus ponens. And I'm going to do the same thing with line 2 and 7, still inside the scope of this vertical sequence. So from lines 2 and 7, I can get G implies I. Okay. That's going to be line 2 and 7 by modus ponens. Okay, look what I have so far. On line 3, it says if I can get F implies I, then I could get J or not H. And we're trying to get J, and we know H is true, so once we break that apart, we can get J no problem. The first thing we need to do to get F implies I noticed that on lines 8 and 9, we have F implies G, but G implies I, so I can get F implies I by hypothetical syllogism from lines 8 and 9. 8 and 9, H, S. Okay. Line 11, don't forget to bring down your vertical line. Once we have F implies I, we can get J or not H. And that's going to follow from, let's see, line 3 and line 10 by modus ponens. Okay, line 12, we're still inside that vertical sequence, so don't forget about that line. Well, we know H is true, but we need the negation of one of those disjuncts on line 11. So we need to do double negation. So from H, we can get not H. And that's going to follow from, let's see, that's going to follow from line 7 by double negation. In order to be able to use disjunctive syllogism, I have to have the not H, the term that I have the negation of, on the left side of that disjunction on line 11. So I need to rewrite line 11 as not H or J. And that's going to follow from line 11 by commutativity. Now I can do that disjunctive syllogism step, still inside that vertical line, to get J. And that's going to follow from line 12 and 13 by disjunctive syllogism. Now look what I've done. Again, just to reiterate, I will use a different color here. I started out by assuming the antecedent of this conditional in the conclusion, E and H. And the goal was to get J on its own line inside the scope of that indented sequence, which I just did. So I'm done with my conditional proof sequence. I can discharge that line. And back outside the scope on a non-indented line is line 15. E and H implies J. And that follows from line 4 through 14, fairly lengthy conditional proof sequence by conditional proof. And again, just to drive the point home, once you've closed off that assumption line after line 14, you can no longer refer to anything from line 4 through 14. Those lines are closed off for use in a longer proof. Okay. Let's do one more example just using conditional proof, and then we'll dive in and do some examples using both conditional proof and the other new proof method, indirect proof. Okay, so here we're given two premises. A implies that B implies that C and not D. It's a fairly lengthy first premise. Kind of scary looking when you first see it. Line 2 says that if you have B or E, then you can get D or E. Okay. And the conclusion we're trying to prove is A and B implies C and E. And because that's a conditional, I'm going to do conditional proof. On line 3, we're going to start an assumption. We're going to assume that the antecedent of that conditional in the conclusion is true. We're going to assume A and B. And the rule we're going to cite is ACP, an assumption for conditional proof. Notice that you don't cite any lines when you're citing ACP, because it doesn't follow from anything above. It's an extra assumption that you're adding into the proof for the purpose of a conditional proof. Okay. Now the goal is to get C and E on its own line inside the scope of this proof sequence. So I'm not sure exactly how we're going to do that yet, but I don't think this will be very hard. Once we have A and B, I suggest we simplify that to get A on its own line. So that's going to be line 3 by simplification. And that gives us the antecedent to that conditional on line 1. So we're going to do modus ponens right off the bat. That'll give us B implies C and not D. So that's going to be line 1 and 4 by modus ponens. Well, I also know that B is true, but I first need to do a commutativity step on line 3 to get B on the left side of that conjunction. So B and A. So that's line 3 by commutativity. We're going to simplify and get B on its own line. Notice at every turn that I'm still bringing down this vertical assumption line. Don't forget about that. So line 6 by simplification. Now I can do another modus ponens step. Right? Line 5 says B implies something. We have B, so we can get C and not D. Okay. And that's going to follow from line 5 and 7 by modus ponens. Now we said we're trying to get C and E on its own line, C dot E, right? The consequent of this conditional in the conclusion. Well, I have C already, right? It's just locked inside this conjunction in line 8. So I'm going to simplify and get C on its own line, still inside that vertical line. So line 8 by simplification. Now I just have to figure out how to get E on its own line. Well, what I see is that the antecedent of the conditional in line 2 is B or E. And I've got B on its own line on line 7. So I can do addition to get B or E, which will give me the antecedent of that conditional on line 2. So this is going to follow not from line 2, but from line 7 by addition. We're just adding that E onto the B. Okay. Oops. Line 11. Now I can do modus ponens. That will give me D or E. So that's going to be line 2 and 10 by modus ponens, still inside the scope of that vertical sequence, which I'm saying a lot today, but I want to really drive that point home. Line 12, continuing that vertical sequence. What I see, if I'm trying to get E now, because remember we said we need to get C and E on its own line. We have C, now we just need to get E. Well, we know D is false because of line 8, and we have a disjunction, D or E. So this is starting to look like a disjunctive syllogism. We just need to get not D on its own line first. So I'm going to rewrite line 8 to get that not D on the left side of the conjunction. Not D and C. And that's going to follow from line 8 by commutativity. We're going to simplify and get not D. Line 12, simplification. And now from line 11 and 13, we know that E has to be true, still inside this vertical sequence. So line 11 and 13 by DS, disjunctive syllogism. But we're not quite done. We said that we assumed A and B is true. That's what we did on line 3. And we were trying to get C and E on its own line. Well, we have C, we have E. We just need to conjoin them together, still inside the scope of this vertical sequence, C dot E. And that's going to follow from line 9 and 14 by conjunction. Okay, I want you to pay attention to what we've got here now. We started out by assuming this antecedent, A and B, on line 3. We've shown that that leads to C dot E on line 15. So we are done with our conditional proof sequence. Line 16 will be back outside the scope of any indented line. It's a non-indented line. And we will have shown now that if A and B are true, then we can get C and E. And that's going to follow. Here's where we have to be really careful. Everything from line 3 all the way through line 15. 3 through 15 by conditional proof. And we are done. Okay, let's move on and do some examples using both conditional proof and indirect proof. So in these proofs from here on out, we can use either or both. We've got two premises in this first example. If K implies K, then R. Line 2 says that if R or M, then N. And we're trying to show that N is true. So what I see right off the bat is that I don't see that I can do conditional proof. There's no obvious conditional that I need here. But what I can do an indirect proof sequence. So I'm going to start out by adding an assumption line. What I'm going to do, I'm going to start out by assuming the opposite of the conclusion. So I'm going to assume not N. And I'm going to cite it here as AIP, an assumption for indirect proof. Now, I just want to remind you what the goal is here. When you do an indirect proof sequence, the goal is to get an explicit contradiction. So I'm going to write this off to the right just as scratch work. We're trying to get something that looks like this: Q and not Q. Some explicit contradiction, a statement that contradicts itself, because what that will show is that if we show that not N implies a contradiction, we will have shown that not N has to be false. In other words, the conclusion has to be true. So we're looking for any substitution instance of Q and not Q. It could be A and not A, it could be K and not K, it could be A and B and not A and B, any substitution instance whatsoever of Q and not Q. So with that in mind, I'm going to erase that, and let's dive in and see what we can come up with. So what I see from here is that assuming not N gives me a nice, easy starting point. I can do a modus tollens step, and that will give you the negation of the antecedent of line 2. So it's not the case that R or M. Okay, that's going to follow from line 2 and 3 by modus tollens. This should look an awful lot like De Morgan's rules. So I'm going to apply De Morgan's rule to line 4 to give me not R and not M. Okay, that's going to follow from line 4 by De Morgan's rule, DM. And all of this should be review at this point. Well, if I can get not R on its own line, then I'll have the negation of the consequent of line 1. So I'm going to simplify line 5 to get not R on its own line. Line 5 by simplification. Again, notice I'm bringing down this vertical line at every step. Well, I can do another modus tollens step, and that will give me it's not the case that K implies K. That's going to follow from line 1 and 6 by modus tollens. I think you can probably see here that the contradiction we're going to get is K and not K. We just need to use the replacement rules to kind of build that from what we have. What I see, when I have a negation of a conditional like this, the thing that comes to my mind is using the implication rule on that conditional, because then I'll have the negation of a disjunction and I can do De Morgan's rule. So let's do that. I'm going to use a material implication. I'm going to leave this outer negation alone and apply the implication rule just to K implies K. That will give me it's not K or K inside parentheses. And that is line 7 by material implication, IMPL, which we haven't used yet today, so it's nice we got an example of that. Okay, on line 9, this is starting to look like a De Morgan's rule step. So we're going to get not K and not K. And that's going to follow from line 8 by De Morgan's rule. Okay, we said we're looking for a substitution instance of Q and not Q, which we almost have here. If we get rid of that double negation in front of the first K, will have K and not K. So that's what I'm going to do. Still inside that vertical line, K and not K, eliminating that double negation. That's line 9 by DN, double negation. Now look what I've got so far. We're almost done. We said we're going to assume the opposite of the conclusion. So if we have the conclusion N, we're going to assume it's negation, not N. That leads to a contradiction. So we're done with our indirect proof sequence. We've shown that our assumption leads to a contradiction. On line 11, we've shown, now here you have to be really careful. We can't just jump right to N. We've shown it's not the case that our initial assumption is true. So in other words, we've shown not N. Now, obviously, that's the same thing as N, but there's a separate step for that, a double negation step. So here, this is going to follow by indirect proof, everything inside that vertical line. And I close it off here to indicate that I'm done with my assumption. And from that point on, I can no longer refer to anything from line 3 through 10. So here we go. This is indirect proof, line 3 through 10 by IP, indirect proof. And one tiny little step left. We don't just need not N, we need N. And we're outside the scope now with that vertical line. So this is on the non-indented line, just line 12, just N. And that's going to follow now from line 11 by double negation, and we're done. So again, just to reiterate how to use indirect proof. When you know you need something, you can start out by assuming its opposite. If it's already a negation, you just assume the positive version. But here we're trying to get N, which is a positive statement. So we're assuming it's negation, not N. We're trying to show that that leads to a contradiction, and an explicit contradiction has to be a substitution instance of Q and not Q. So if you can get something like Q and not Q on its own line, you'll have shown that that initial assumption is contradictory, that that assumption can't be true, which is what's happening here on line 11. So on line 3, we started out by assuming not N. We've shown that that leads to a contradiction, K and not K. In other words, if not N were the case, K would be true and K would be false, which is absurd. So we know that our assumption, not N, has to be false. That's how we get not N on line 11. And then finally, we used one tiny little double negation step at the very end to convert that to the conclusion N. Okay, let's do some more. Excuse me. So here we've got two premises. We've got H implies, L implies K. On line 2, we have L implies that K implies not L. And we've got a conclusion, not H or not L. I don't see a really obvious starting point here, so I'm going to try to do an indirect proof. I'm going to try to show that if the conclusion were false, that would lead to a contradiction. So on line 3, I'm going to assume the negation of that entire conclusion inside of a vertical sequence. It's not the case that not H or not L. AIP, assumption for indirect proof. And now we just want to start applying rules and try to get an explicit contradiction. Again, what we're looking for now is something like this, Q and not Q. When we find something like that, we'll be done with our indirect proof sequence. Well, right off the bat, I see that we can do De Morgan's rule on line 3. And that will give us not H and not L. Line 3 by De Morgan's rule. Of course, we have a couple of double negations there. So on the next 2 lines, I'm going to get rid of those double negation steps, still inside this vertical sequence. Let's get rid of the first one, H and not L. Line 4 by double negation. And then we're going to get H and L. Which is line 5 by double negation. Okay, this is really nice because once we have H and L, those are the antecedents of those conditionals on line 1 and 2. We just need to get H and L on their own line. So I'm going to get H on its own line on line 7 by simplification. Compressing this a little bit so I can have more room on the right side of the screen. We need to get L on its own, but first we need to do commutativity, so L is on the left side of that conjunction. So I'm going to rewrite line 6 as L and H. That's going to be line 6 by commutativity. Then I'm going to simplify to get L on its own line. So this is line 8, simplification. Okay, now I'm going to start doing these modus ponens steps that I said I could do. Still inside this vertical sequence, don't forget about that. Let's see, so from line 1 and line 7, I can get L implies K. That's going to follow from line 1 and 7 by modus ponens. And from line 2 and 9, I can get K implies not L. And that's going to follow from 2 and 9 by modus ponens. Okay, I'm going to move up to the top right of the screen here. Line 12, again, be really careful. Don't forget about it. You're still inside this vertical indirect proof sequence. What I see is that on line 10 and line 11, I've got L implies K, but K implies not L. So I'm going to do hypothetical syllogism to get L implies not L. Line 10 and 11 by HS. Excuse me. Well, I know L is true on line 9. So from line 9 and line 12, I can get not L. And that's going to follow from line 9 and 12 by modus ponens. And I'm very nearly done, right? On line 9, we said L is true, but on line 13, we said L is false. There's our explicit contradiction. All we have to do now is conjoin them together. So we have an explicit contradiction, a conjunction consisting of a statement and its negation on the same line. So I'm going to take line 9 and 13 to get L and not L. And that's our substitution instance of Q and not Q that we said we were looking for. So 9 and 13 by conjunction. Okay, look what we've got. We started out by assuming the negation of the conclusion. And we said, well, if that leads to a contradiction like Q and not Q, in this case we got L and not L, we can close off that indirect proof sequence. And in line 15, outside the scope of any indirect proof sequence, we're going to get, here's where you have to be really careful. You can't jump right to the conclusion. We've shown it's not the case that our assumption is the case. So whatever we had on line 3, we're going to write the negation of it. So not, here in parentheses, not H or not L. Be careful of those negations. So this is going to be line 3 through 14 by indirect proof. And all we have to do now is get rid of those double negations. So on line 16, not H or not L. And that's going to follow from line 15, 15 by double negation. And we're done. So again, this is a classic example of how to use indirect proof. If we didn't see any other starting point, we didn't have H and L already. We couldn't do modus ponens. No obvious starting point. But what we could do is assume the conclusion is false, which is what we did on line 3, and show that that leads to a contradiction. Then we will have shown that that initial assumption is false. That's what this extra negation is here on line 15 by indirect proof. One more double negation step, and we're done. Okay, that one wasn't too bad. Okay, here we're given two premises. Not A implies B and C. Line 2 says D implies not C, and we're trying to show a conditional. D implies A. Because that's a conditional, I'm going to start out by doing conditional proof. I'm going to assume D is true, the antecedent of that conditional. ACP, assumption for conditional proof. Now what I'm going to do, there's probably another way to do this, but this is a more fun way. If I'm trying to get A from there, that's the goal of doing a conditional proof. You start out by assuming the antecedent and you're trying to prove that the consequent follows. Well, if I know I need A, I'm going to try to get that by indirect proof. So here on line 4, I'm going to start a new indented sequence inside the first one. And if I'm trying to get A, I'm going to assume not A. And here you have to be really careful. Assumption not for conditional proof, but for indirect proof. So what I'm looking for now inside that second sequence is a substitution instance of Q and not Q. If I can get that, that will show me that A has to be true and not false. Then I can close off my conditional proof to get D implies A, and we'll be done. So with that in mind, let's move forward. Once I have not A, I can do a nice, easy, friendly modus ponens step with line 1. So from line 1 and 4, I can get B and C. That's going to follow from line 1 and 4 by modus ponens. Friendliest rule ever. Okay, we're trying to get a contradiction. What I see is that I've got C here on line 5. I just need to simplify it out. And I can also get not C on line 2 because I know D is the case, or I assume that D is the case on line 3. So let's start there. Let's do modus ponens with line 2 and 3, and that will give us not C. From 2 and 3 by modus ponens. Okay. But we know C is true because of line 5. We just need to simplify that out. We're going to have to do a couple little preliminary steps. We need to get that C on the left side of that conjunction. So I'm going to rewrite line 5 as C dot B. And that follows from line 5 by commutativity. I'm going to simplify to get C on its own line, still inside those two vertical lines. Line 7 by simplification. Now remember what I'm looking for. I'm looking for an explicit contradiction, Q and not Q. In this case, I know C, I know not C on line 6. I need to conjoin those together, C and not C. That's an explicit contradiction. Okay, that's going to be from line 6 and line 8 by conjunction. A couple more steps and we're done. So remember why we assumed A was false. We said we knew we were going to need A once we assumed D. So we said, let's assume A is false and see if that leads to a contradiction, which it does. So now I'm going to close off that inner indirect proof sequence, still inside this first vertical sequence. Don't forget about that one. And we've shown not A. It's not the case that our assumption was the case. So that's going to be indirect proof from line 4 through 9, IP. But of course, not A is just A. So on line 11, still inside this vertical line, A. And that's going to follow from line 10 by double negation. I'm going to bump this up one row. There we go. We said that we started out by assuming D is true, so we can try to show that A follows from that. Well, we've done that. On line 3, we assume D. Inside that same vertical line, we get A. So we're done with our conditional proof sequence. Close that off. On line 12, on a non-indented line, we can get D implies A. And that's going to fall from everything inside that first vertical line that we started, from line 3 through 11 by conditional proof, CP. And we are done with that one. So this is a great example of how you can use an indirect proof inside of a conditional proof or vice versa. Like if you know you need something, try getting it by indirect proof if you don't see a more obvious way to get it. And sometimes when you start a conditional proof, remember what you're doing. You're assuming the antecedent, trying to prove the consequence. So that's what's going on here. We started out by assuming the antecedent. We said, okay, now we need A. But we didn't see an obvious way to get it. So we said, okay, let's try to get A by indirect proof, but inside that outer conditional proof. Then all we have to do is discharge those two assumptions, close off our indirect proof sequence, close off our conditional proof sequence, and we're done, and we'll have the conditional proof that we needed, or the conditional that we needed. Okay, let's do another one. So here we've got 3 premises. Not M implies in and O. 2 says in implies P. 3 says O implies not P. And we're just trying to show that M follows. I don't see any reason to do a conditional proof here, at least not yet, if we need one at all. But I don't see an obvious starting point either. And that's a red flag that maybe you should start to think about an indirect proof. So what I'm going to do, I'm going to assume that the conclusion is false. Assume not M. And that's going to be AIP, assumption for indirect proof. And now, just to be really clear, what I'm looking for is something like this, a substitution instance of Q and not Q, a statement and its negation, because that will show that our initial assumption has to be false. So let's get going and see if we can find one. On line 5, I see an obvious starting point. I can do modus ponens to get N and O. And this is the nice thing about doing conditional proof and indirect proof is you get a lot more easy rules. Modus ponens steps, commutativity, double negation, De Morgan's rule, those kinds of steps. Once in a while, you'll have to do a constructive dilemma or a distribution step, maybe an exportation step somewhere, but you'll find you'll do a lot more easy rules when you start using conditional proof and indirect proof. Okay, so this is going to be from line 1 and 4 by modus ponens. Well, N and O is great because those are the antecedents of the conditionals on lines 2 and 3. I just need to simplify N and O. Let's do that. Let's simplify N right off the bat. That'll give us, let's see, that's from line 5 by simplification. In order to get O, we have to do a commutativity step, so O is on the left side of that conjunction. So line 5, commutativity. And on line 8, we're going to get O on its own line. From line 7 by simplification. Okay, on line 9, still inside this vertical sequence. In fact, let's do both together. Let's do line 9 and 10. We said we're going to need to do 2 modus ponens steps. We have the antecedent of the conditional on line 2. We have the antecedent of the conditional on line 3. So let's do some modus ponens steps. From line 2 and 6, we can get P. Okay, that's line 2 and 6 by modus ponens. From line 3 and line 8, we can get not P. Three and 8 by modus ponens. Okay, so notice now we've got P and we've got not P, but we're not done with our indirect proof sequence until we get them on the same line conjoined together. So it's an explicit contradiction. So I'm going to bump this up just a little bit. On line 11, still inside this vertical sequence, I'm going to conjoin 9 and 10 together to get P and not P. A statement that obviously contradicts itself. So that's going to be line 9 and 10 by conjunction. Now look what I've got. We started out by saying, okay, we need the conclusion M, so we're going to assume not M. We've shown that not M leads to a contradiction, which means that not M cannot be the case. So we know, here's where we have to be careful. You don't just go right to M, you get not M. It's not the case that our assumption is true. And that follows from line, let's see, everything from line 4 through 11, everything inside that indented sequence, 4 through 11 by indirect proof. And our very last step, which I'm going to do here off to the side, outside the scope of the vertical line, because we just closed off that vertical line, just M. And that's going to follow now from line 12 by double negation, and we're done with that one. Piece of cake. This one was even easier than the last one. Okay. In this next example, we've got only one premise, just K, and we're trying to show this conclusion. If S, then if T, then S, or S implies that T implies S. Let's get started. So the conclusion is a conditional. It says if S, then that expression in parentheses. So let's start out by doing a conditional proof. We're going to assume the antecedent of that conditional S. And that is by ACP, an assumption for conditional proof. The goal then is to get this expression in parentheses, T implies S, inside the scope of that vertical line. But what I see right off the bat is that that itself is another conditional. So I can do another conditional proof inside this one to get that conditional. So on line 3, I'm going to introduce yet another vertical line. I'm going to assume the antecedent of that conditional, just t. And I'm going to get that from ACP, assumption for conditional proof. And now I'm going to use a different color just to make it really clear. I'm looking for this. I'm looking for the consequent of that conditional, just S. Well, I already have S, but I don't have a rule that lets me bring that down or rewrite that. But what I have to do is some fairly arbitrary technique. It's a little ugly looking, but it's a consequence of the rules that you're given inside this textbook. I can go from S to something like S and S, or S by tautology. So from line 2 by tautology. And then I can do tautology in reverse to go right back to S, which is really silly and tedious. But again, it's a consequence of the rules that you have in this book. This textbook does not give you a reiteration rule that lets you take a line and write it subsequently later in the proof. So you've got to do some wacky thing like this, kind of arbitrary tautology step, even though we know S is already true, or assumed it's true on line 2. So from S and S on line 4, again, we know S has to be the case. So yet another tautology step, line 4 by tautology. Little trick of the trade there. It's kind of an ugly step, but it's elegant in a way. Just do a step and then undo it really quickly. Okay, so look what I've got now. We said we're going to start out by assuming S on line 2. We're trying to get T implies S, but we said that's another conditional. We need to build that conditional. So we're going to assume the antecedent of that, assume T on line 3, and then we're going to try to prove S, which we just did on line 5. So we're done with this inner conditional proof line, still inside the scope of the first one. Be really careful not to lose that one. We've shown T implies S inside the scope of that first conditional proof line. So this one's going to follow from line 3 through 5 by conditional proof. Now we've shown from line 2 through 6 that if we assume S, we can get T implies S inside the scope of that line. So I'm going to close off that conditional proof sequence. And line 7 is back on a non-indented line outside the scope of both of those sequences. S implies that T implies S. And that's going to follow from line 2 through line 6 by conditional proof. And we're done. That was a very short proof. Okay, just a few more. I think you'll see these rules are a lot of fun. Once you learn these techniques, these proofs go really quickly. The things that would be really hard to do in section 7.3 and section 7.4 of your textbook are now almost trivial once you have conditional proof and indirect proof. Okay, let's see what we can do here. We have two premises. If K or L, then M and N. Line 2 says if N or O, then P and not K. And we're trying to show that K is false. So I don't see an obvious way to use conditional proof. I don't see an obvious starting point with the premises that I have. So I'm going to jump right into doing indirect proof. I'm going to assume that K is true inside a vertical indented sequence. Okay, that's going to be AIP, assumption for indirect proof. And again, I know I'm being a little pedantic about this, but I really want you to remember this. Once you do an indirect proof sequence, you assume the opposite of what you're trying to prove, and then you're trying to show that it leads to a contradiction, an explicit contradiction like Q and not Q, some substitution instance of that statement. Okay, not sure how we're going to get there yet. I can kind of see it in advance, probably better than you can because I've been doing this longer, but let's just dive in. I think from here, we don't have to worry about it very much. If we just start churning away using the rules that we have, we're going to get to the conclusion. Get to an explicit contradiction and be able to discharge this indirect proof sequence pretty easily. So I see we have K. The antecedent of the conditional in line 1 is K or L. I can get that by addition onto K. So K or L. That's going to follow from line 3 by addition. That gives me the antecedent of the conditional in line 1. So I can do a modus ponens step, still inside this vertical sequence. That will give me M and n. That's going to follow from line 1 and 4 by modus ponens. The next thing I see is that, well, if I could get in on its own line, I could get the antecedent to the conditional in line 2. I could get in or o by addition. So let's do that. Let's do commutativity on line 5 so I can simplify and get in on its own line. So n and m. Line 5 by commutativity. I'm going to simplify and get in, not forgetting my indented vertical line. Line 6 by simplification. And we said we were doing that so we could do addition to get in or o. And that's going to follow from line 7 by another addition step. Okay, from there we can do modus ponens to get p and not k. From line 2 and 8 by modus ponens. And if you didn't see it already, here's the contradiction we're looking for. We know, or we've assumed k to be true on line 3, but that leads to p and not k. So we know k would have to be false as well. We just need to simplify not k out and then conjoin it together with that k. So on line 10, I need to do commutativity to get not k on the left side of this conjunction, not k and p. Line 9 by commutativity. I'm going to simplify out not k, still inside this vertical line. Line 10 by simplification. Okay, line 12 is still inside the vertical line. Don't forget about it. We've shown now that if k is the case, we can get not k. We need to conjoin those two together now. K dot not k, k and not k. So that's going to be line 3 and line 11 by conjunction. And that's the explicit contradiction we were looking for, a substitution instance of q and not q. Okay, so we are going to close off that assumption line. And line 13 is back outside the scope now. We are not inside that indented sequence anymore. So on its own line, line 13, we've shown the opposite, or the negation of our initial assumption. If we started out by assuming k, we've shown from lines 3 through 12 that k has to be false, not k. And this would follow from lines 3 all the way through line 12 by indirect proof. And we're done. Okay, pretty straightforward. So again here, just to reiterate, a good time to use indirect proof is if you obviously don't see any starting point. And here, if we're trying to assume not k, we just assume the opposite of it. We're going to assume k is true, show that that leads to some contradiction, any contradiction at all, a and not a, b and not b, a implies b and a does not imply b, so on and so forth. And then that will show that the initial assumption has to be false. So we close off that vertical line, back outside the scope of it on line 13 here, and we've shown that our initial assumption k has to be false or not k. Okay, next proof. We only have one premise, just f, and we're trying to show either G implies H, or it's not the case that G implies J. So I don't see a really obvious starting point here. Obviously, the letters G and H and J are not inside the premises. You could start thinking about adding those in by addition, but I think you're going to get stuck and find that that's not very fruitful. So because there's no obvious starting point, I don't even see a conditional that I really need to be able to do anything else. I'm going to try to do this entire proof by indirect proof. So this is going to look a little wacky, a little wild, a little unwieldy, but if you follow along, I think you'll see it goes pretty quickly. So what I'm going to do on line 2, I'm going to start an assumption line. I'm going to assume that the entire conclusion is false. So I'm going to put a bracket around the entire thing and put a tilde in front of it. It's not the case that the entire conclusion, G implies H, or not G implies J. Okay, all of that in a bracket. And I'm going to cite that as AIP, Assumption for Indirect Proof. And I'm going to try to show that this leads to a contradiction now. If I can do that, then I can discharge my indirect proof sequence. I will have shown that this initial assumption is false, so I'll get not, that expression in brackets. I'll do a double negation step, and we'll be done. So let's do that. Even though this is pretty scary looking, I'm going to use another color here just to draw really explicit attention to this. We put a negation in front of this entire bracketed expression, but this is still just a negation of a disjunction. So we can do De Morgan's rule on this, which I'm going to do right now. So I'm going to do, it's not the case that G implies H, and it's not the case that not G implies J. Okay, so that is line 2 by De Morgan's rule. Just to be really explicit, treating G implies H as P in De Morgan's rule and treating not G implies J as Q in De Morgan's rule. Take a look at the rule and take a look at what I just did there if you're stuck and don't see why that works. Okay. On line 3, still inside the scope, line 4, not line 3. On line 4, still inside the scope of this vertical sequence, I'm going to start simplifying these terms out and see if I can get some sort of a contradiction. So I'm going to simplify the left-hand term right off the bat. It's not the case that G implies H. Okay, so line 3 by simplification. I'm actually going to do the right side as well because I suspect that my contradiction is going to be G and not G, because that's the term that's in both of those two parenthetical expressions. I don't know for sure, but I suspect that that's probably going to be the case. So I need to do commutativity first. So I'm going to rewrite line 3, switching around the order of that conjunction. It's not the case that not G implies J, and it's not the case that G implies H. And that's going to be line 3 by commutativity. Line 6, still inside that vertical sequence. I'm going to simplify and get not G implies J. It's not the case that not G implies J. So line 5 by simplification. Okay, line 7, still inside the scope of this vertical line. In fact, I'm going to extend that down. We're going to need this for at least a few more lines. So in line 4, I've got the negation of a conditional. And like I said previously in the video, whenever you see something like that, one thing you can do is apply the material implication rule to that conditional inside the parentheses. And if you do that to line 4, you're going to get this. It's not the case that not G or H. And that's going to follow from line 4 by implication, IMPL. And I'm actually going to do the same thing to line 6. I think you'll see why here in a moment. If I do that, I'm going to get, it's not the case. Now here you have to be a little careful, not G or J, because we already had that negation in front of the G there. So we're going to end up with that extra negation. Okay. That's going to follow from line 6 by implication. And I'm actually going to get rid of that double negation, I think. So let's rewrite 8 as it's not the case that G or J, just to clean things up a little bit. So line 8 by double negation. Okay, oops, excuse me. Line 10, still inside the scope of this vertical sequence. What I see on line 7 and line 9 is now I can do a couple of De Morgan's rule steps. Like line 7 is the negation of a disjunction, so is line 9. So I'm going to do 2 De Morgan's rule steps on line 10 and 11. Just in tandem so you can see where I'm going with this. So if I do De Morgan's rule on line 7, I'm going to get not G and not H. So line 7 by De Morgan's rule. And I'm going to do the same thing on line 9. That's going to give me not G and not J. Line 9 by De Morgan's rule. Okay, I don't have much room to work with here, but I think I can squeeze it in on the right side of this page. On line 12, still inside the scope of this line, I'm going to start simplifying these two terms that have G in it out. So I can get not G from line 11 by simplification. From line 10, I can get not G. And that's going to follow from line 10 by simplification. Now, I actually could conjoin these two together. I could conjoin not G and not G, because that itself is a substitution instance of Q and not Q. It's a statement and its negation. But just to make it look a little more elegant, I'm going to get rid of that double negation. This isn't kind of an unnecessary step, but it'll make the end result look a lot prettier, which is a nice aspect to have inside of a proof. So I'm going to rewrite line 13, get rid of those double negations. That's going to be line 13 by double negation. On line 15, we're still inside the scope of this vertical line. Don't forget about it. We're going to conjoin line 12 and 14 together, G and not G. There's our explicit contradiction we were looking for. So that's line 12 and line 14 by conjunction. Now that I have my explicit contradiction, I can close off my indirect proof sequence. Line 16 is back outside, and we've shown that our initial assumption is false. In fact, I'm going to scroll down just a little bit here to give us some more room. We said we started out by assuming the negation of this entire expression in brackets. So on line 16, way down here, I'm just going to kind of give myself a little more room. On line 16, we've shown that initial assumption is false. So again, you can't go right to the conclusion. You've shown that the assumption is false. So it's not the case that it's not the case. And here's that long expression in brackets that we started with. G implies H, or not G implies J. Close off that bracket. And now that's going to follow. Let's see here. We started the assumption on line 2. So it's line 2 through 15 by indirect proof. And all we have to do now on line 17 is get rid of those double negations. And we will have shown G implies H, or not G implies J. That's going to follow from line 16 by double negation. And we're done. And that is, I have to scroll here so you can see it, but that's the conclusion that we started trying to prove, which we got here on line 17. Okay, that was kind of a lengthy one, but it wasn't too bad. We just needed one fairly long indirect proof sequence. And you see, from there, it was pretty straightforward. Simplification, commutativity. The two key steps here were these implication steps that you may not have been able to see, so make sure you pay attention to what I did there. Double negation, De Morgan's rule, simplification, simplification, double negation. Really easy rules all the way throughout. It just took a fairly large number of steps. Okay. Next example. We've got three premises. If N or O, then C and D. Line 2 says if D or K, then P or not C. Line 3 says if P or G, then it's not the case that N and D, and we're just trying to show that N is false or not N. I think this will go pretty straightforwardly. So I don't see an obvious starting point, which is a red flag that you should use indirect proof. So if I'm trying to show not N, I'm going to start an assumption. I'm going to assume N is true. And then I'm going to try to show that that leads to a contradiction. So this is AIP, assumption for indirect proof. Okay, what I see right off the bat is that by addition, I can get N or O, which is the antecedent to this conditional on line 1. So that's line 4 by addition. I'm going to go pretty quickly through this one. That'll give us C and D by modus ponens from line 1 and 5 by modus ponens. And I'm going to do the same trick to get the antecedent to the conditional on line 2. If I know C and D is true, I'm going to get D, and then I'm going to add K onto that using addition. But I need to get D on its own line first. Wrong color, which I have a tendency to do here for some reason. I'm going to reverse the order of the conjunction on line 6 to get D and C. Line 6 by conjunction. Simplify D out. So line 7 by simplification. And like I said, we're going to do addition to get D or K, which will give us the antecedent to that conditional on line 2. D or K. And it doesn't follow from line 2, that follows from line 8 by addition. Okay, that gives us P or not C by modus ponens. So line 10, still inside this vertical sequence, we're going to get P or not C. That's 2 and 9 by modus ponens. Okay, what I see here is that I've got a disjunction on line 10, P or not C, but I know C is actually true, not false. That's what line 6 tells us. I just need to get C on its own line first so I can do that disjunctive syllogism step that we're seeing. So I'm going to simplify line 6 to get C on its own line. 6 by simplification. Okay, line 12, still inside the scope here. I have to do a couple steps before I can do disjunctive syllogism. I need to get that term, not C, that's on the right side of that disjunction, line 10, on the left side. And I need to do double negation on line 11, so I have not the opposite of one of those terms, but I have the negation of one of those disjuncts on line 10. So we got a couple preliminary steps we have to do that we can't skip over. So I'm going to rewrite line 10 as not C or P. And that is going to follow line 10 by commutativity. I'm going to come over here and continue our vertical line. We're on 13, but still inside that vertical line. I'm going to do double negation on line 11 to get not C. So line 11 by double negation. Now I can do a disjunctive syllogism step to get P on its own line. Should all be review. If you need to, back up a week or two and look at the rules of implication and the rules of replacement from the rest of chapter 7. That's going to follow, let's see, from line 12 and 13 by disjunctive syllogism. And I'm going to do that addition trick again. Now that I have P, I can do addition to get P or G, which is the antecedent to that conditional on line 3. So that is from line 14 by addition. That will let me do a modus ponens step to get the consequent of that conditional. So it's not the case that N and D let's see, so that's line 3 and line 15 by modus ponens. And that looks like De Morgan's rule to me. We have the negation of a conjunction. So if I do De Morgan's rule, that will give me not N or not D. So that is line 16 by De Morgan's rule. 18, still inside the scope of this line. It's a pretty long proof, but we're still inside the scope of that one indirect proof line that we started. So let's see what we've got. I see we have not N or not D, but on line 4, we know that N is actually true. So this is starting to look like a disjunctive syllogism step. I just need to do a double negation step first so I can use disjunctive syllogism correctly. That would give me not D, but I know D is true because of line 8. So there's our explicit contradiction. We know we can get D and not D. So let's do what we just said we'd do. We're going to do a double negation step on line 4 to get not N. So line 4 by double negation. Then we said, by disjunctive syllogism, we know not D from lines 17 and 18 by disjunctive syllogism. And finally, now in line 20, we have our explicit contradiction. We know we have D and not D. And that would follow from line 8 and line 19. The proofs are getting a little longer, as you can see. 8 and 19 by conjunction. Oops, use the pink color. There we go. 8 and 19 by conjunction. So look what we've done. We said we need to prove not N. That's the conclusion. So we're going to assume the opposite of it. If we're trying to show N is false, we're going to assume that N is true. And then we're going to try to show that that leads to a contradiction. After many, many steps here, we've got D and not D, an explicit contradiction inside the scope of that vertical indented sequence. So we're going to, wrong color. We're going to close off this indirect proof sequence right here. Again, I like to use this horizontal line, which the book does not use, but I think makes it really clear what's going on. And on line 21, outside the scope of that indented sequence, we've shown that that initial assumption N has to be false. So line 21, not N. And that follows now from lines 4 all the way through line 20 by indirect proof. And we're done with this proof. Not too bad. I think you can see that even though this is a long proof, look how easy these rules are. Addition, modus ponens, conjunction, simplification, addition, modus ponens, simplification, commutativity, double negation, disjunctive syllogism, addition, modus ponens, De Morgan's rule, double negation, disjunctive syllogism, and conjunction. Really, really easy rules, even though there are a lot of steps to this proof. So I hope this proof in particular makes the case that even though the proofs can be really lengthy, look how easy this proof was once we started out by assuming that N is true. It should all have been reviewed from that point onward, as long as you know how to close off the indirect proof sequence correctly. Okay, I've got 2 more proofs for you. Let's do the penultimate proof. This one is pretty scary looking, as I wrote it here on the screen. We've got 2 premises. K implies that long expression in brackets. M or N implies P and Q. Line 2 says, if L, then that second long expression in brackets, Q or R, implies S and not N. And we've got a conclusion we're trying to prove. If K and L, then not N. So because the conclusion is a conditional, I'm going to start out by doing a conditional proof sequence. So on line 3, I'm going to make an assumption. I'm going to assume the antecedent of that conditional, K and L. And I'm doing that for conditional proof. So we're going to cite it ACP, assumption for conditional proof. Now here's where you should pause and think about what you're doing. If we know we're trying to get not N, right, this is what we're doing. We're doing a conditional proof. We're assuming the antecedent of the conditional, K and L, so we can get not N. Now I do see a couple of obvious starting points here. I see that I can do modus ponens steps with line 1 and 2 once I simplify K and L out. But in order to try to speed this proof along, I'm going to try to prove the consequent of that conditional, not N, by an indirect proof sequence inside this conditional proof sequence. So on line 4, I'm going to add another assumption line right here. Make sure you don't forget about adding these vertical assumption lines. If we're trying to prove not N, once we've assumed K and L, I'm going to assume N. And then if I can show that that leads to a contradiction, I'll be able to close off that indirect proof sequence. That'll give me K and L implies not N. Okay. Oh, I'm sorry, I forgot to cite the rule here. That's going to be AIP, assumption for indirect proof. Okay, let's get going now. Right off the bat, I think the thing that's easy to see is that if we simplify K and L, get K on its own line, L on its own line, we can do a couple modus ponens steps with lines 1 and 2. So let's get k on its own line. I'm going to try to write small because I think this is going to be a fairly lengthy proof. So k on its own line, that's going to be line 3 by simplification. And on line 6, continuing both of these vertical sequences, I need to reverse the order of the conjunction in line 3. So L is on the left, so L and K. That's going to follow from line 3 by commutativity. Line 7, continuing our vertical sequences, we're going to get L on its own line. That's going to be line 6, simplification. Okay, so that's going to let me do a couple modus ponens steps. From line 1 and line 5 now, I can get that entire expression in brackets inside line 1. So I'm going to get M or N implies P and Q. And that is going to follow from line 1 and line 5 by modus ponens. Okay, line 9, continuing my vertical sequences. I'm going to do the same thing with line 2 and 7. That will give me Q or R implies S and not N. Okay, that's going to follow from line 2 and 7 by modus ponens. Okay, the next thing I see is that if I could get M or N, the antecedent to that conditional on line 8, I could do a modus ponens step. Well, I already have N on line 4, so I'm going to add M onto that with addition. Oops, not with that color though. So on line 10, still our 2 indented lines here. N or M. And that's going to follow from line 4 by addition. But in order to be able to use modus ponens, I need to do commutativity on that so it matches the antecedent to line 8. So I need to change that to M or N. So line 10 by commutativity. Line 12, we're going to do that modus ponens step. That'll give us P and Q. That's going to be modus ponens from line, let's see, line 8 and 11. Okay, line 13. Still inside our 2 vertical lines, don't forget about those. What I see next is that if I could get Q on its own line, I could add R, and then I'd have the antecedent to the conditional on line 9. But in order to get Q on its own line, I need to do commutativity on line 12, so Q is on the left side of that conjunction. So on line 13, I'm going to get Q and P. And that's going to follow from line 12 by commutativity. Okay, line 14, I'm going to simplify that and get Q. So 13, simplification, oops. Okay. We said we were doing that so we could add R onto Q by addition, so Q or R. So line 14 by addition. Line 16, still inside our 2 vertical lines. We're going to do modus ponens to get S and not N. Let's see, that would be line 9 and 15 by modus ponens. Line 17, got to squeeze it in there, sorry about that. I see the contradiction we're going to get here. On line 4, we have N, and line 16 says S and not N. So if we simplify not in out, we'll get N and not in, and that'll be our explicit contradiction that we were looking for. And then I'll talk about how to wrap this up here in just a moment. But let's get not in on its own line first. I need to do a couple things first. I need to reverse the order of the conjunction on line 16 to get not in on the left. So not in and S. And that's going to follow from line 16 by commutativity. Okay, in line 18, I'm going to simplify the not in out. So 17 by simplification. And now I've got my in, I've got my not in. I just need to conjoin them together, still inside these two vertical lines, in and not n. And this is going to follow from line 4 and 18 by conjunction. Now I'm going to scroll up a little bit here, so we're going to lose our premises, but just try to follow along. So we said we started out by assuming K and not L with the goal. I'll scroll. There we go, just a little bit so you can still see it. We started out by assuming K and L, and we're trying to prove not N. So we started out by assuming K and L, and an assumption for conditional proof on line 3. We said, okay, now we need not N. So we're going to try to get that by indirect proof. So we're going to assume N is true and try to show that that leads to an explicit contradiction, which we finally got here on line 19. So I'm going to close off that innermost indirect proof sequence. And here you have to be really careful. I'm still inside the scope of that first conditional proof sequence that we started. So on line 20, I will have shown not N. And that follows from this inner proof sequence, line 4, all the way through line 19, 4 through 19 by indirect proof. But we said, okay, we were ultimately doing a conditional proof. We were saying we're going to start out by assuming K and L up here on line 3 and try to show that that leads to not N, which we finally got on line 20. So now I can close off that conditional proof sequence. Line 21 will be back outside all of the proof sequences, and we will have shown that if we assume K and L, then we can get not N from that, and that would follow from this entire conditional proof sequence from line 3 all the way through line 20 by conditional proof CP, and we're done. Okay, so that one wasn't too bad, but another classic example of how you can kind of pair up using a conditional proof sequence and then using an indirect proof sequence to get the consequent of the conditional that you need to build in your conditional proof sequence. Okay, let's do one more proof, and this is the last thing I have for you guys for today. Okay, so we have two fairly scary looking premises. Line 1 says, if F then we have another if-then statement inside that. C implies C implies G. So if F, then C implies C implies G. It's kind of an unwieldy statement. Line 2, we've got if G, then that long expression in brackets. H implies that E implies H, and all of that implies K and not K. And the conclusion we're trying to show is just not F. So I don't see an obvious starting point with the premises. They're really massive and scary looking and unwieldy. So I'm going to start doing an indirect proof sequence. If we're trying to prove that F is false, that's what the conclusion is, I'm actually going to assume that F is true. And I'm going to try to show that that leads to a contradiction, because that will show that F would have to be false then. So AIP, an assumption for indirect proof. Okay, and this gives me a really obvious starting point. I can do modus ponens with line 1. That will give me everything inside that bracket. C implies C implies G. Okay, this is going to be line 1 and 3 by modus ponens. So at this point, I'm a little bit stuck, but what I see is that line 4 is a conditional. It says if C implies C, which is kind of self-evident, everything always implies itself, then G. But what I need in order to be able to do modus ponens to get G, I need that conditional, C implies C. So this is a great example of like the second you recognize that you need a conditional that you don't see how to get, try thinking about using a conditional proof sequence to get it. So on line 5, I'm still inside the scope of this first sequence. I'm going to try to prove that C implies C to build that conditional that I need so I can do a modus ponens step. So I'm going to add a new assumption on line 5. I'm going to assume C as an assumption for conditional proof, trying to get C, which is obvious, but I need to do it in the sequence of steps and using the rules that we've got. Then I can close off that conditional proof sequence, and that will give me C implies C. So here's our tautology trick one more time that we did earlier in the video. I don't have a way to rewrite this line subsequently on the proof. Again, some proof systems and some textbooks have that. This book does not have that. What I can do though is this. If I have C, I can get C, or C and C, that would be fine too, by tautology on line 5, by tautology. And then I'm going to do the same exact rule in reverse, which is a little pedantic and silly, and you might laugh at this and go, this is really pointless, but this is the only way to power through this using the rules that you've got. So I'm just going to rewrite that again as C by tautology in reverse. So line 6 by tautology. Okay. So we said we needed this conditional, C implies C. In fact, I'm going to highlight it in blue so you can see it. We said we needed this conditional, C implies C, so we could get G to keep this proof moving forward. Well, we just did that. We assumed C and we got C again inside the scope of that conditional proof sequence. So I'm done with this inner conditional proof sequence now, but I'm still inside the scope of this outer indirect proof sequence that we had started. So on line 8, I can close off that conditional proof sequence and get C implies C. That's what happened. I assumed C on line 5 and I managed to get C on line 7 inside that second indented line. So this is going to follow from lines 5 through 7 by conditional proof. Now again, just to be really clear, I've said this a few times in the video, but I want you to take this point home. Whenever you've closed off an indented sequence like this, a conditional proof sequence or an indirect proof sequence, you can no longer cite any of the lines inside that sequence. So now that I've closed off this conditional proof sequence, I can no longer refer to lines 5 through 7 anywhere in the proof. That's very important. Okay, line 9 is still inside this outer indirect proof sequence. Excuse me. I said that if I could get C implies C, then I could get G by modus ponens. Now I have C implies C, so I can get G by modus ponens. And that would follow from line 4 and line 8 by modus ponens. Great. Line 10, still inside the scope of that line. But line 2 says that if G is the case, I can get this really long expression inside the brackets or the curly braces. So I know G on line 9, so I can get everything inside those curly braces, which I'm going to write here. H implies E implies H. All of that implies K. Oops, I forgot a square bracket there, right there. K and not K. I'm trying to write a little small to pack it in there. That's going to follow from line 2 and 9 by modus ponens. Okay. What then do we do? What I see is that I see an explicit contradiction kind of packed inside line 10. I see K and not K. In order to get that out, I need the antecedent to those conditionals, to that conditional. I need everything in the left bracket there. H implies that E implies H. But those are conditional. So I'm guessing I'm going to do an indirect proof, or excuse me, a conditional proof sequence, maybe 2 packed together here in order to be able to build the left side of that conditional on line 10. So let's start that. I'm going to scroll down here. If we have to scroll back up and down, that's okay. So I know I need the left side of this, this conditional on line 10, but that itself is a conditional. So I'm going to start another conditional proof sequence. I'm going to start out by assuming H. Again, we have to start a new assumption line here. Assume H on line 11. And that's going to be ACP, assumption for conditional proof. Now the goal, once I've done that, is to get E implies H. I think that's pretty clear, right? If we're trying to get H implies E implies H, we assume H. Now we're trying to get that little expression in parentheses, E implies H. But that in itself is another conditional. So what I'm going to do, this is going to look a little scary. I'm actually going to add a third assumption line here. So now I've got 3 lines going. Got to keep track of these. If you lose track of these, you will prove something that doesn't actually follow. So I'm trying to get E implies H. To do that, I'm going to assume E by another conditional proof, ACP. And now if I can get H inside that line, I can close that off to get E implies H. I can close off the second one to get H implies E implies H. And then I'll get my explicit contradiction into my indirect proof line, and we'll be done with this proof. Okay, so in line 13, we're inside 3 assumption lines now. So it's a little scary looking, but I hope you're keeping track of why I'm doing what I'm doing here. So if I need H, I can't just bring it down, but I can do that tautology trick. So I'm going to do H or H, and that's going to follow from line 11 by tautology. And then I'm going to do a reverse tautology to get that back down to H. Making sure I don't lose track of these assumption lines. I'm inside 3 different assumption lines there now. H. And that's going to follow from line 13 by tautology. I'm going to keep scrolling up here. If we have to scroll back up to see something, that's okay. So line 15, we're still in 3 assumption lines. Make sure you bring those down. Oh, excuse me. We don't need that third one. Let me back up just a little bit. There we go. So we said we were trying to get E implies H, which we just did. We've assumed E on that third assumption line. We got H inside that line. So we're done with that one. We'll close that off and we'll get E implies H. And that's going to follow from lines 12 through 14 by conditional proof. And why were we doing that? We said, well, we're going to start out by assuming H and try to get E implies H on that assumption line, which we just did. So we're done with that conditional proof line. Still inside this outer indirect proof line. So we can get H implies that E implies H. Now here you have to be really careful. We assumed H on line 11. We closed off that assumption line on line 15. So this is line 11 through 15 by conditional proof. Still inside this outer assumption line. We said, okay, if we could get what's inside the brackets on line 10, I'll use a different color so you can see it here. We said we're trying to get everything inside this bracket so we can do modus ponens and get our explicit contradiction. So I'm going to do that next. That's going to give us K and not K, which is happily what we were looking for, an explicit contradiction. And that's going to follow from line 10 and 16 by modus ponens. And finally, we're done. Not quite done. We have one more step, but I'm going to scroll up so you can remind yourself how we started here. We said, okay, we're going to try to do this whole proof by indirect proof. Let's start out by assuming F is true, since we're trying to prove F is false. And if we can show inside that long outer vertical line that goes all the way down to line 17 that we can get an explicit contradiction, which we just did, we'll be done. And we will have shown that our initial assumption, which is F, has to be false. So way down here on line 18, not F. And that's going to follow from, I have to remind myself which line we started with, line 3, all the way down to line 17. So line 3 through 17 by indirect proof. And we're done after 18 steps. So I just want to reiterate something about the last part of this proof. Whenever you see that you need a conditional, but you don't know how to get that, start out by doing conditional proof. Assume the antecedent and try to get the consequent. But if that consequent itself is a conditional, then you can do a conditional proof inside to build that conditional. Start out by assuming the antecedent of that, try to prove the consequent. Then you just have to close off those conditional proof sequences, starting on the inside and working your way outward until you prove the conditionals that you needed to prove. Again, very important to keep in mind that once you've closed off a sequence, you can no longer refer to the lines that make up that indented sequence. So on lines 12 through 14, I just proved E implies H on line 15, but I can no longer refer to lines 12 through 14 anywhere else in the proof. Once I've closed off the conditional sequence that ends on line 16, right? H implies that E implies H. I can no longer refer to lines 11 through 15 anymore inside the proof, and so on and so forth. That's very important because, again, the things that are indented are not actually true. They might be, but we don't know for sure. They're true only if you assume that the line that starts the indented sequence is true. We don't know if they're true just from the premises themselves. Anyways, I hope this is a fairly long video. We did a lot of examples. I hope these two proof techniques are helpful to you. I think you'll find that if you go back and try some of these proof techniques on some of the proofs you had to do in section 7.3 and 7.4 of your textbook that were really hard to do at that time, that some of those become almost trivial when you introduce conditional proof and indirect proof. Even if these proofs get pretty long, I think you can see that look how easy these rules are. We did modus ponens and tautology and modus ponens again. We did really easy rules, even though the proofs are pretty lengthy and fairly scary looking because of these nested assumption lines. Get lots of practice on these. Again, just as a reminder, for your homework for this week, cover both section 7.5 and 7.6 of your textbook, 2 sections in one here. There's only about 20 proofs to do in total for your homework this week, but get lots of practice. Go slowly through this video if you need to, and definitely be in touch with me by email or by phone if you have any questions or concerns. We can always jump on a Zoom meeting and I can walk you through some things. We can look at anything together, but make sure you master everything in chapter 7 because it's very important that as we move on to chapter 8 that you have all of chapter 7 mastered before we move on. So please, please, please get lots of practice and definitely let me know if you have any questions. Other than that, hope you guys have a great week and I'll see you a week from now in the next video.